All right, let's get right into it. For decades now, we've been launching these incredible robotic explorers out into the solar system. But here's the thing, these are way more than just scientific field trips. What we're going to do here is connect the dots and show you how every single one of these missions is basically the training ground for humanity's next giant leap, space mining.
You really have to think of this as a cosmic treasure hunt. See, asteroids are kind of like the crumbs left over from the cosmic bakery when our solar system was first forming. And they are packed with amazing stuff, water, precious metals, and even secrets about where we came from. So yeah, right now, science is in the driver's seat, but you can bet that commerce has its eyes glued to the rearview mirror.
At the end of the day, the goal is to turn what looks like space junk into really useful stuff, like rocket fuel or industrial metals. And to get there, every single one of these science missions is basically a crucial research and development phase. Step by painful step, they're proving that we can actually navigate the void, land on these tiny, low-gravity worlds, and handle potentially hazardous materials millions of miles from home.
So how do we get from just looking at asteroids to actually mining them? Well, it's not one giant leap. It's more like a journey. A steady climb up this maturity curve. We're going to walk through the first 3 big steps today, starting with prospecting using simple flybys, then moving to surveying with orbiters, and finally, assaying by actually bringing samples home. Let's start at the very beginning.
Welcome to Level 1. This is all about scouting. Before you commit to a long, super expensive operation, you got to send your scouts out ahead to see what's what. And in space, our scouts are the flyby missions.
So what is a flyby? It's basically a cosmic drive-by. You don't stop, you don't even slow down much, you just get a quick peek as you zoom on past. It really is like glancing at a menu before you decide what you want to order for dinner. It's a fast, relatively low-cost way to catalog what's out there and identify the most promising targets for the more complex missions down the road.
And you know what? Even a quick peek can reveal some huge surprises. On its way to Jupiter, the Galileo probe spotted something absolutely incredible. A tiny moon, which they named Dactyl, orbiting the asteroid Ida. This was the very first time we'd ever seen an asteroid with its own moon. That was a total game changer. It told us asteroids can have their own little satellite systems, which, for a future miner, is both a potential hazard you have to navigate and maybe a bonus resource right next door.
Okay, so our scouts have found a place that looks interesting. We can't just send in the heavy equipment yet. We've done our prospecting, so now it's time to survey. It's time to go from that quick glance to a long, hard stare.
And that brings us to Level 2, the orbiter. These are the missions that don't just fly by. No, they settle in for the long haul. They actually go into orbit around their target, sometimes for years, creating these incredibly detailed 3D maps.
And the difference in the data we get is just staggering. It's night and day. A flyby gives you a few seconds of information, basically a flat 2D picture. An orbiter, on the other hand, gives you years of data. You can map out its gravity, figure out its density, all in 3D. And that's absolutely critical because you can't land a billion-dollar mining rig if you don't know whether the surface is solid rock or, a cosmic sinkhole of loose gravel.
And we've had some real trailblazers here. Near Shoemaker was the first to ever orbit and even land on an asteroid. It proved its target, Eros, was a solid object with stable ground. Then came Dawn, this incredible interplanetary road tripper. It used these hyper-efficient ion thrusters to visit 2 different worlds. And it confirmed that Ceres has vast amounts of water ice, basically a potential rocket fuel depot just sitting there in the asteroid belt.
And get this, right now, NASA's Psyche mission is hurtling towards what might just be the ultimate jackpot. We think it's a metal world, the stripped-down, exposed core of an ancient planet. If it's as rich in iron and nickel as we think it is, this single body could be worth trillions of dollars. So this isn't just a science mission, it is the ultimate commercial prospecting survey.
Okay, so we've scouted a target with a flyby, and we've mapped it in incredible detail with an orbiter. There's really only one thing left to do to prove we know what we're dealing with. We have to climb to the final and frankly the most difficult step on our current technological ladder. Actually go there, touch it, and bring a piece of it all the way home.
This is Level 3, which you might call the holy grail of asteroid exploration, the sample return mission. It is the ultimate test of our robotics because it's not a one-way trip. You have to launch, travel millions of miles, land, grab a sample, take off again, and, the hardest part of all, survive a fiery re-entry to get that precious cargo back to Earth. And the very first to pull this off was Japan's Hayabusa mission. I love this one. It's the Plucky Pioneer. Its mission was defined by just incredible resilience. It had to travel to this tiny football field-sized asteroid called Itokawa and do something no one had ever done before, bring back a physical sample.
But wow, what a journey it was. I mean, everything that could go wrong pretty much did go wrong. The spacecraft suffered fuel leaks, its engines failed, it had communication blackouts, it even got zapped by a solar flare. But against all odds, it literally limped back to Earth and dropped its sample capsule into the Australian outback. Inside, just 1,500 microscopic grains. A tiny amount, but a truly monumental achievement.
So, learning from that nail-biter of a mission, Japan launched Hayabusa 2. And this was basically Hayabusa on steroids. It didn't just touch its target, an asteroid named Ryugu. No, it actually bombed it. It fired a copper projectile to blast a fresh crater. And that let it get to the pristine material underneath, which, it turns out, contained water and amino acids, the actual building blocks of life.
Then came NASA's OSIRIS-REx, which was basically a cosmic vacuum cleaner sent to the asteroid Bennu. And Bennu had a massive surprise waiting for us. We expected a solid rock. Instead, the spacecraft found this fragile, active world, a sort of fluid pit of plastic-like balls that literally sneezed rocks into space the moment the collection arm touched down. It was wild.
Just look at this. This shows you the unbelievable leap in technology in just over a decade. In 2010, Hayabusa's historic return gave us microscopic dust, stuff you could barely see. By 2023, OSIRIS-REx came home with a jar literally full of rocks and dirt. We went from analyzing tiny grains to studying handfuls of the stuff. In total, OSIRIS-REx brought back 70.3 grams from Bennu. And that might not sound like a lot, but it absolutely smashed its original goal of 60 grams. It's the largest sample ever returned from beyond the moon, and it is packed with clues about the birth of our solar system.
So, let's step back. What does all of this add up to? Well, each and every mission, from the simple flyby to the incredibly complex sample return, has been systematically building the skills, the technology, and the raw knowledge we need for commercial space mining.
And we're even learning an entirely new skill: heavy engineering in deep space. NASA's DART mission was like a cosmic billiard shot, a kamikaze spacecraft sent to intentionally crash into an asteroid. The result? A smashing success. For the first time in history, humanity changed the course of a celestial body. Now, this is huge for planetary defense, obviously, but it also proves we can physically move asteroids around, a key technology if you want to nudge resources to where you need them.
So here it is, the cheat sheet of what we've learned so far. We've discovered that some asteroids are solid rock, but others are just loose piles of rubble. We've found hidden water ice and the building blocks of life. And we learned, the hard way, that some surfaces are surprisingly active and fluid. We've gone from just being passive observers to being active participants out there.
So the next time you pick up your phone, think about this for a second. The rare metals inside it, stuff like platinum, might one day come not from a mine deep in the Earth, but from an asteroid floating in space. And thanks to these robotic pioneers we just talked about, that future is a whole lot closer than you might think.